Hello, class. Welcome back. This is lecture 4. Today, we're going to learn about other tools for limits of sequences or seeing if they converge or diverge. So the idea is that so far, we looked at sequences and we used tools from Calc 1 to see the limit of these sequences. But we just modify it a little bit to make it work for sequences, but it really comes down to doing the same stuff you did in Calc 1. And so then this would tell us whether the sequence converges or diverges, because that's the goal, is to figure out whether they converge or diverge. So next, other sequences where we can't use previous tools. So it's good to start with stuff that you can do using old tools, but you do got to learn some new stuff. So here's a sequence that we can't really handle with Calc 1, something like this: 4 to the n over n, and then this exclamation point is called factorial. So you may remember what a factorial is, but I'll just remind you. So what is this sequence? Well, if I start at 1, actually, I'll start at 0 just to remind you of what 0 factorial is, which is important. Okay, so if I start at 0, then 4 to the 0 is going to be 1, and 0 factorial is also 1. If you need a way to remember that, it's how many ways you can choose something. So there's only one way to choose 0 things, and that's to not choose it at all. So that's why there's 0 factorial is 1 is one way to think about it. But in any case, the next term would be 4 over 1 factorial, 4 squared over 2 factorial, 4 cubed over 3 factorial, and so on like that. And so remember that factorial for bigger numbers, so this is going to be 1 over 1 is 1, 4 over 1 is 1. Factorial for bigger numbers means multiply all the previous numbers together. So 2 factorial means 2 times 1. So then this is 16 over 2 is 8, I guess. And then this would be 4 cubed is 64 over 3 factorial is 3 times 2 times 1, which would be 6, and so on like that. Okay, so something like this, we can't use our old tricks because n factorial does not correspond to a function. There's no such thing as f of x equals x factorial that you learned about in Calc 1. So we can't think about derivatives. We can't think about like L'Hopital's rule, or you could think about the squeeze theorem maybe, but mostly you're out of luck. Okay, and it's because we just don't know how to deal with derivatives of something like this. So what we need is some new stuff. And it really just comes down to defining new things that show up. So the first thing is this: a sequence is called bounded above. So we need a nice mathy way that matches our intuition. We need a nice mathy like way to say that something is bounded above, that matches what we think about when we say those words. So what it should really mean is just that it's everything in the sequence after a certain point is smaller than something. So how do we say that? If there's a number, this magic number that's going to be so big that it's bigger than everything in the sequence, after some point, we'll call it M. And what does it do? Well, it does what I said, except in math symbols, AN, the terms in the sequence. I guess I should have named the sequence earlier. Let's do that. The terms in the sequence are going to be bounded by it, meaning below it, because it's bounding the numbers above. So all the numbers are smaller than this bound for all n after some nth term. Okay, so for example, it's just a lot easier to work with examples. So here's a specific sequence 1 over n. This is bounded by a lot of stuff, but one specific number that bounds it above is just the number 1. So it's because, according to this definition, if you think about the terms in the sequence, 1, 1/2, 1/3, 1/4, and so on like that, you need to think about, is it true that this happens? Is it true that they're less than 1? After a certain point, yes. In fact, right away, they're all less than or equal to 1. So after which term? After the first term. So it has a 1 less than the bound, a 2 less than the bound, a 3 less than the bound, forever. So they're all starting from the very beginning less than or equal to the bound. So that's why they are called bounded above. The sequence is called bounded above. Meanwhile, there's the opposite. So a sequence is called bounded below. It's going to be very similar to what bounded above, except the opposite. If there's a very fancy number, we'll still call it M, and it's going to be smaller than everything this time because it's bounding it below. It's bounding the sequence below. So all the numbers in the sequence after some point are going to be bigger than this bound. Okay, so it looks very similar. So for example, we can use 1 over n again. This one's a bit trickier to see, but this is bounded below by 0, for example, because if you think about these terms, 1, 1/2, 1/3, 1/4, and so on, every single one of them has that they are bigger than 0, bigger than or equal to 0. Let me put the 0 on the left, since that's what I have up there. That's my lower bound. So 0 is less than or equal to every single thing, starting from the beginning. It doesn't have to be from the beginning, but in this case, it is again. So that's nice. Okay, so having a bounded sequence is going to mean having both of these at the same time, and that's going to be extra nice when that happens. Just a couple more examples. So something like this is bounded. See if you could think about it real quick on your own, but it's bounded below by what? By 0. And it's also bounded above by 1. So you can make lots of other examples, and we'll see lots of more once we bring in other things to talk about too. Okay. So now let's see what happens when we get both. So a sequence is called bounded if it's bounded below and above. Otherwise, it's called unbounded. And now we want to see, like, what does this have to do with being a sequence being convergent or divergent? So first, some examples. So 1 over n is bounded. We already showed that by showing it was bounded above and below. Meanwhile, 2 to the n is unbounded because it's not bounded above. It is bounded below by 0 because it just starts at 1 and then it goes 2, 4, 8, 16, and so on. So it's not bounded above because you can never pick a number big enough. You can pick as big as you want. You can pick 1,000 and you can say, like, this is bigger than everything in there, but it's not. It's not bigger after some nth term because all I have to do is go further out in the sequence and eventually I will surpass that bound. I just haven't written enough. I've only written 5 numbers, but once I get to a certain point, I will surpass that bound. And no matter what bound you try to make, I can always surpass it by going further in the sequence. So that's why 2 to the n is unbounded. So unbounded sequences are nice because it tells you right away that they diverge. So an unbounded sequence must diverge. So right away, for example, we could say 2 to the n diverges. But it doesn't matter that it's 2 to the n, it matters that it's unbounded. And visually, you could sort of think about it like this. The terms in the sequence are sort of like these little dots that you get by plugging in whole numbers, 1, 2, 3, 4, and so on. And if they don't have a bound above and below, then that means one of 2 things. Either they'll always be going up and up and up, and therefore they won't be going towards a number, or maybe they'll be going down and down and down, and also for that reason won't be going towards a number. So the green and the blue here are 2 unbounded representations of unbounded sequences as pictures. But what about if it's bounded? Does that mean it automatically converges? The answer to that is no. There's more to it. So a bounded sequence does not automatically converge. You need more. And visually we could see it, or we could see an example. So here's an example, -1 to the n. We've already actually done this one in the last video, and we've said why it diverges just by looking at it, because it bounces back between -1 and 1 forever. So this diverges because it doesn't go towards a specific number, but it is bounded by -1 from below and 1 from above, because you could say -1 is less than or equal to all the terms, and that's less than or equal to 1. But it diverges because these numbers don't go towards a single number. They go towards two single numbers. And so visually, it's sort of just like this. We have 1 and -1 that are our bounds that the sequence will never go past. But just because they never go past it doesn't mean they actually go towards something, which is what's happening here. Okay, so just because it's bounded does not mean it diverges. We need something additional for it to converge. Sorry, I think I said diverge, but let me say it again. So just because it is bounded does not mean it converges. You definitely need something else to make sure it converges. Okay, and this is an example of why. All right, so that's the question. When will a bounded sequence converge? Well, if you could say something else about these blue dots, then that's what we're looking for. And here's the property that we need. A sequence is called increasing after some term. A capital N is going to represent the specific number for which you would say the term is increasing. So what would it mean for a sequence to be increasing? Well, you just think about it as going up. The numbers are going up. But we want to say that in a more mathy way that we can use. And one way to do that is to compare terms with previous terms. So how can I do that? Well, if I had like A1, A2, and A3, what would it mean for the sequence to be increasing? Starting at A1, it would mean that A1 was smaller than A2 because it got bigger, it increased. And then A2 was smaller than A3, and so on like that. So we want to make use of these less than or equal to's to say what it means for something to be increasing. And what it means is that AN and AN plus 1, if we compare them, that's just one term and the next term. It should be that the next one is the bigger one. So that should happen. But we're only saying it's increasing after this very special number. So it's not always increasing, maybe. At the beginning, maybe it's not. But where the index is bigger than or equal to that number, that special number. Okay, so this just means like increasing past n specifically. All right, so again, definitions are hard to work with. You got to see examples to really make sense of them. So let's see an example and then think about why this definition means that the sequence is increasing. Okay, so here is a specific example. So 1/2, 2/3, 3/4, 4/5, 1/6, and so on. That's the pattern. That's my sequence AN. So let's show that AN is increasing after, but we don't know specifically what capital N is. So maybe I'll put a question mark there, but we're going to figure it out as we show it's increasing. Okay, so the trick is, first, we need a nice simple formula to describe this, because I can't just look at every two and say, yeah, okay, A1 is smaller than A2, Okay, look at this one. Yeah, that's smaller than A3. I can't just do that forever. So what I need is the nice formula for AN, which in this case, I can do pretty quick. It's just N over N plus 1, starting at 1, right? If I plug in 1, I get 1 over 1 plus 1 is 1 over 2. If I plug in 2, I get 2 over 2 plus 1 is 2 over 3. So I get the sequence I'm after. So here is what I need to deal with. And so all we do is compare AN and AN plus 1 now. Okay, so what's AN? Well, AN is just this, because this is the representation of the nth term. So AN is N over N plus 1. What's AN plus 1? That's just the next term, which really means take N and replace it with N plus 1. So this N that was there on top is becoming N plus 1. And the N on the bottom is also becoming N plus 1. So we get something like that, which we can simplify as N plus 1 over N plus 2. And so what we need for this to be an increasing sequence is that AN, which is N over N plus 1, is less than or equal to N plus 1 over N plus 2. And so we got to figure out why this is true. So why is this true? But also for what values of N? And to do it, you just need to simplify it. So it's really not that bad. At this point, you just cross multiply. And so you get N times N plus 2 less than or equal to N plus 1, N plus 1. And we're just trying to work it until we get to something that we can say is for sure true. So if I simplify, I get N squared plus 2N over there. And on the right side, I get N squared plus 2N plus N on the right. And then if I subtract on both sides, oh wait, sorry, I get N squared plus 2N plus 1. Forgot my basic algebra. Okay, and then if I subtract N squareds, subtract 2 N's, I just get 0 is less than or equal to 1. And so at this point, you say, like, is this true? First of all, or you say, when is this true? Let's say it like that. Actually, that's better. Let's say, when is this true? When is 0 less than 1? Well, always. So what that means is that this thing is also always true. And so now we can say that this guy is definitely less than this guy always, but always meaning for which values of N? Well, the first value right away is true because it's always true. So what you would say is that this sequence that we started with is increasing after A1 because this was true immediately. Sometimes what you'll get here is only true after a specific value of N, and then that will change this last thing. So we'll do an example like that as well. Okay, but next let's do the opposite of increasing, which is decreasing. So similarly, a sequence is decreasing. It's just going to be the exact opposite thing after a specific term. if now you want the next term to be the smaller term. So an plus 1 needs to be smaller than an, because that means that the next term is smaller than the previous term. So the terms are getting smaller. That's what it should mean to be decreasing. So as long as you're past, this is what this is saying, as long as you're past this special number n that you have to figure out. So this really means like decreasing after nth, capital Nth term. Okay, so we'll see an example right away just to see how this works. Okay, so for example, 4 to the n, this is the one we looked at the beginning, over n factorial is decreasing after A3. So this one's a bit trickier because when I wrote out those terms at the beginning, the first couple actually got bigger. And it's because it's only decreasing after A3. So it's not decreasing right off the bat. It's not getting smaller right from the first term. And we'll see it this time. We'll actually be able to see it by showing it using this same type of argument. Okay, so same exact type of argument. You compare an plus 1 and an. This time we put them in the other order because we're showing decreasing. Okay, so what's an plus 1? That's just the n plus 1th term. That just means plug in n plus 1 for n. So that n becomes n plus 1 up there. Now on the bottom here, people always have trouble with factorials. You're replacing n. You're not just sticking a 1 after, you're replacing it. So that n that was there became this, n plus 1, and then you still have the factorial. Okay, so do not do this, n factorial, and then plus 1. Okay, because that's completely different. That's not replacing n with n plus 1. That's not plugging in n plus 1. That's just adding 1 to a number. Okay, so that's that. And then an is just the nth term, which we have the formula for already. So that's that. Okay, so now all we're really doing is checking when this one, the n plus 1th term, is less than or equal to the nth term by making it be less than or equal to, and then simplifying and seeing if we get some sort of constraint about when this is true. Okay, so let's simplify it. Again, pretty much always going to cross multiply. But in this case, you're actually going to want to cross multiply and divide. So I'm going to divide this 4n that way. Actually, I'm not going to cross multiply at all. I'm only going to divide. I should have said, oh, actually, no, I'm going to do both. Okay, I'm going to divide the 4 to the n that way. And then I'm going to multiply the n plus 1 factorial up that way. And of course, there are other ways you can simplify it. I'm just giving you an efficient way that I've done ahead of time that I know will work. But you could try something else and it could work. Okay, so then simplify this on the left. What happens here? If you have two numbers with the same base divided by each other, you just have to subtract the powers. N plus 1 minus n. That's just going to give you 4 to the 1 is 4. Okay, what about on the right here? It's a bit trickier if you don't remember factorial stuff. Let's write it out. So n factorial means n times the previous number. What's the number before n? Well, the number before 6 is 5 because 5 is really just 6 minus 1. So it's really just whatever your number on minus 1 is the previous number. And then if I want to go to the next previous number, I got to subtract another 1. That takes me to n minus 2. And I'll just keep doing that until I get to the 1 at the very end. And on top, the only difference is I'm starting with n plus 1 as my first number. So what's my next number when I subtract 1, n plus 1 minus 1 is really just n. But then after that, n minus 1 to get the previous number is n minus 1, and then n minus 2, and so on until you get to the end at 1. And so what's happening here is that these are the exact same thing, except the top has one extra term. And so these all divide out, and you just get left with this n plus 1. So that's a nice little shortcut for dividing two factorials. You write out the terms and see if they secretly cancel, like in this case. Okay, so when is n plus 1 bigger than 4? It's not always true. So it's not like 1 was bigger than 0, which is always true. Well, it's true. If I just subtract by 1, I can see when it's true. It's when n is bigger than or equal to 3. So what this is saying is that our original inequality here, it's not always true, but it is true when you get past 3. Once you get past 3, then it's true. So what this is saying is an plus 1 is less than or equal to an, and the magic number, capital N, turns out to be 3. That's what capital N is. It's this number that you're trying to figure out, basically. Okay, so then to conclude, this sequence is decreasing, because that's what we showed here, after, not always decreasing, it's only decreasing after A3. And that's what we showed by getting this thing. Okay, so that's one increasing, that's one decreasing. So there's lots of examples that all work very similarly. So I'll do a couple more just to try to help you out. So let's try this one. N over 2 to the n is decreasing after A1. So that means that the very first term compared to the next term, it's gonna get smaller immediately. So let's do it more quickly. Now that we have the foundation, so the idea is right away you should know decreasing. That means I need my an plus 1 to be the smaller one, and so I need to compare these two in this way, and then I just got to plug in n plus 1 on the left, so this becomes n plus 1 over 2 to the n plus 1, and on the right it's just n over 2 to the n. Okay, then you simplify as much as possible. In this case, I'll divide the n on the left that way, and I'll multiply the 2 to the n plus 1 up that way. It doesn't matter which order. In fact, I could have done this a different way that would be faster. Okay, so then on the right, these cancel and you just get 2. So in fact, it would be better if I put that n back where it was before and I multiply it back over there. I should have left it there because this is a little easier to deal with. And now if I subtract the n over, I get 1 is less than or equal to n. So then this tells me that the sequence that we started with, what was it, n over 2 to the n, is decreasing after A1. So again, this is my capital N because it's telling me when is this true? Only if you're past 1, and that's saying that's when this is true, which is saying when this is true, which is saying when it's decreasing. All right, let's try another one. Some of these can be a bit tricky. Let's see if I put in any tricky ones for myself here. I might have. So this one is increasing. after, I'll just leave it blank and we'll just see if we figure it out. Okay, so it is supposed to be increasing. So now I got to check if an is less than the next one, because the next one is supposed to get bigger. So I want to check this way. So what do I do here? On the left is just an, so it's just keep the nth term exactly the same. And on the right, I need to replace n with n plus 1. So I'll get that and that. Okay, so then these can be a bit trickier to simplify. So let's see, what can we do? Well, the factorials you always want to put together. So let's do that. How do I want to do it? Let's see. Let's do, let's put the n plus 1s to the fifths over here by multiplying it up. And let's put the n factorial down there by dividing it down. And now these cancel just like they did in the previous example that I did with factorials. This just becomes n plus 1, just like before. Oops. So what can I do? Well, I can divide this n plus 1 down because, and then I'm going to multiply this n to the fifth up, because then I can cancel one of the n plus 1s. So I get n plus 1 to the fourth is less than or equal to n to the fifth. So when is this true? This is tricky. Let me think. Do I know when this is true? This is tricky. Let's see. Yeah, so there's no easy way to see exactly which value of n this happens for. So the basic idea is that, okay, you have a fifth power here and a fourth power here. So this one will be bigger eventually, maybe not right away, but it's actually hard to, it would take a very long time to see which value of n it's actually bigger for, because I would need to like multiply this out, which would take a very long time. So let's just leave it at this. Let's just say that we did show it's increasing, but it's too much work to be specific about after which value. Okay, but yes, n to the fifth will eventually be bigger than n plus 1 to the fourth power. Okay, and there might be some simple trick that I'm forgetting off the top of my head, but I do want to do one more that is a different type of problem and show you the trick for this one. So let's do it. This one definitely will have a nice ending instead. Okay, so this one is increasing after, I believe it's going to be increasing right away. So let's do A1. Okay, so I need to compare just like always. If it's increasing, I need the next one to be the bigger one than the previous one. So I need it to look like that. So the left side will be n to the n over n factorial. The right side, so again, it's a replacement. So I'm changing this n to n plus 1, but I'm also changing the power to n plus 1. And then down here, I have n plus 1 factorial again. Okay, so now we're going to move things around. Let's see, I'm going to move the factorials that way and the powers that way, so that on the left side, it'll cancel just like before. So this is just n plus 1 again from how I did it before. And then the trick is to notice that n plus 1 power means that I have n of them, but I have one more, because when you add powers, that means you're multiplying the same base. So this is really this. And then I can divide this one over. So I'm going to divide that over. And that'll cancel with the one that's already on the left. And then on the right, I have this. So I have 1 is less than or equal to n plus 1 over n, and I can just have them both to the n power because they're being divided by each other. So I can take out the n power through that division. And then I can get rid of this power by doing the 1/nth power on both sides. And because n over n is 1, and 1 to the 1 over n is really just 1 as well. I end up with this. So finally, I end up with this by multiplying that n over and then subtracting, I get that. So again, this is always true. So what that means is it's independent of what n is. And that means that the sequence is increasing, or if it was a different problem, decreasing right at the start, right at A1, because we're no longer depending on n like in other examples. Okay. So these are the most common types of increasing, decreasing examples. You may run into other ones. Ones like the one I didn't finish, you're not going to run into, just because I'm not going to put them on there. Because when you have powers mixed with factorials like this, if the power is really big, like 5 or even 4 or 3 are kind of big, then you always end up with something like this, where one is clearly bigger than the other because it has a bigger power, but algebraically it's not nice to simplify like the other ones were. But just be aware of those. Okay. So those are all the increasing, decreasing examples. What do those have to do with convergence? So now we can finally say that after all those examples. And so this is what it is. If you have a bounded decreasing sequence, then it must converge. So before, remember, we said a bounded sequence might not converge. It doesn't have to. But if you add in decreasing, it definitely will converge. I should just say actually bounded below. And there's an opposite as well, a bounded above and increasing sequence must also converge. So here's the pictures for why these make sense. So if you are bounded below, so here's your bound, capital M is what we called it, and your sequence is decreasing, that means it's going down, down, down after some point. Let's just pretend right away on the first term in this drawing. But because it's bounded, it can never go past this number. But because it's always going down, it is going to continue to go towards that number. So it will converge to M because it decreases toward the bound. It specifically decreases towards like something more specific, like the best bound that there is. But the point is, if it has a bound, it's got to decrease towards something. without going past it eventually. And so you just get stuck going towards it. Similarly, the opposite case, if you have your bound above, and so let's do this one. In this case, it might not be increasing right away. That's fine. Maybe it only decreases after the 5th term or increases after the 5th term. But as long as there's a place where it starts increasing and becomes an increasing sequence, then after that point, the same type of thing will happen. It'll converge to M because it's going to increase toward the bound. So in the examples that we've done, so for example, we did this one, but it was increasing after A1. This one is actually unbounded. So it doesn't matter that it's increasing, it's going to still diverge. But this other one, it was decreasing after A1. And it's also, you could see that it's bounded below by 0. So it'll have to converge. It can never go below 0 because none of these things will ever be negative no matter what you plug in as you go on and on. So because it's decreasing and because it can't go past 0, it's got to converge. And let's see another one. Do we have another one here I can refer to? Yeah, so this one we did much earlier, n over n plus 1. This was increasing after A1. And it's bounded by 1, bounded above. So it's going to also converge because the terms are going up and up and up, but they can't seem to get past 1. So they just get closer and closer, and that becomes their limit as you go down the list of terms. So again, it's because it's both bounded and increasing for above, or bounded below and decreasing. And then that's enough to converge. I think we did one more that I can reference. So this one as well was decreasing after A3, but it's also bounded below by 0 because it can never be negative. So this one also converges. Same idea, except the first 2 terms actually go up, but then at the 3rd term, it starts to go down, down, down forever. And so it's got to converge because it's not ever going to pass the bound. It'll just go towards the bound. Okay, so that is it for today. If you want a keyword for what this is called, monotone convergence theorem. It's the name of this type of thing. Okay, so see you next time.